I wanted mainly to talk about, let me remind you where we were. Okay, what we'd done is, in principle, understood the construction of scattering amplitudes in the bosonic string completely. This was in principle because we didn't do any scattering amplitude calculations. We just gave the prescription, and you don't understand anything unless you've done a calculation. But we postponed that for later. We postponed that till after we understood the superstring. Okay? Let me remind you what the structure of the bosonic string scattering amplitudes were. The structure was this, that you had to do some sort of path integral over dx, dB, and dc. Okay? Then you had an action. This action was an action for the scalars, the b's, and the scalars, the b ghosts and the c ghosts. And this action had vertex operators, and it had other insertions. You remember the details of this? Most of these vertex, if you had many such insertions, most of the vertex operators were integrated vertex operators. Okay? Most of them came B to Z. However, there were some vertex operators which were fixed vertex operators, fixed at particular positions. And they came with a C ghost insertion, the CC bar. I've written 3 of them because on the sphere we needed 3. Okay, the number depends on which genus we're in. Okay, in addition, on a generous genus gene manifold, there are the manifold itself has moduli. Okay, and so there was an integral over the moduli, and then there was an insertion associated with each modulus, which was basically B del G by del T. Okay, this was the structure of the string scattering amplitude. Okay, the vertex operators carried all the information of the states we were scattering. Okay, this is the thing that we went through in great detail when we went through the BRST cohomology. There was one-to-one correspondence between states, between BRST cohomology classes and physical states. Okay, on this set of BRST equivalences, we showed that there was a positive definite inner product, and we showed that the set of BRST cohomology inequivalences was in one-to-one correspondence with the set of states in light cone quantization. Okay, which was the physical spectrum of the string. Okay, so this thing here, one is free to put these vertex operators. One is free to put these vertex operators in any cohomology. Well, as I wrote the formula, the answer for the scattering amplitude, the answer that came in a more straightforward way, went this way. These, you remember, there was a one-to-one. There was one choice of cohomology class elements. Okay, there was one choice of cohomology class elements in which, associated with every cohomology class, there was an element which went like C tilde times a dimension of 1, 1 primary. This 1, 1 primary was not unique. There were equivalences even in this 1, 1 primary things. Things that were both null states, things that were both descendants as well as primaries. Anyway, all that, you remember all that. So, in this formula, the most straightforward derivation of this formula gets you this 1, 1 primary either here to be integrated, or C tilde times this 1, 1 primary is explicitly put here. But because there was a BRST freedom, because this whole path integral had an invariance, enjoyed an invariance under BRST transformations, you could do more complicated things. And we'll explore some of these more complicated things that will make our life easier when we study the superstring. Here is a very natural canonical choice. As you will see, there are less natural canonical choices with the superstring, associated partly with this and partly with the thing called pictures that we'll discuss in great detail over the next few classes. Okay, our goal was to develop a similar formula for the superstring. So to complete the analysis of this formal problem, so what are the formal elements? First, we want to understand the analog of this formula. Second, we want to understand the analog of the BRST cohomology. The set of vertex operators, what are the vertex operators that go into this formula, what is this formula, and so on. Okay, that is the thing that we're heading towards. Okay, so at the end of the last semester, we did 2 or 3 things. The first thing we did in some detail was to study free fermions. The action for free fermions was just, you remember we wrote down a set of Pauli matrices such that Dirac matrices, under which this action here simply turned into psi plus del minus psi plus psi minus del plus psi minus. This was in Lorentzian space, then we analytically continued, and we called psi plus psi, and this psi minus we called psi tilde or psi bar, I can't remember which. This is completely holomorphic. So let's say that our conventions are such that this goes to cell di cell psi del psi bar psi plus psi tilde del z bar del z psi tilde. Okay, the equation of motion of this for this field makes del z bar psi 0. So psi is a completely holomorphic field. The equation of motion for the other guy makes del z psi tilde 0, so it's completely anti-holomorphic. This guy was a dimension half 0 field, and psi tilde was a dimension 0 half field. All this you remember, right? You remember that now the basic idea behind the superstring was that we're going to change the matter action on the superstring, but much more importantly than that, change the symmetry algebra of the superstring of the world sheet. You see, the symmetry algebra that was used in our BRST quantization, the thing that appeared in the BRST charge, was the stress tensor, associated with the fact that what we were gauging was Virasoro symmetry. Okay, this was associated with the fact, for instance, one way of saying this is that our physical states were associated with Virasoro primaries. Okay, so anything that was a Virasoro descendant was not physical. Virasoro means under LMs. Do you remember our operator had to be a primary field of dimension 1, 1? Why did it have to be primary? Can somebody tell me? Why not just any 1, 1 operator?
We got these conditions.
From BRST quantization we got these conditions. Yes, but more physically intuitively. Just looking at this path integral, where did the primarily primarality condition come from? What is the symmetry that forces it to be primary?
It has to be a tensor. It has to transform as a tensor.
Yeah, and very importantly, it has this whole formula has to be invariant. Diffeomorphism is good, but scalars are all all scalars under diffeomorphism. Wild transformations. What I've not written here is factors of square root g. Okay, because factors of square root g.
That was also important for this on-cell condition.
What? On-shell condition? Yes, it's related.
That was related to the dimension, and then on-cell condition forced it.
Yes, it's related. It's related. The fact that it's a 1-1 primary is the same as the on-shell condition.
Yes.
But where did that 1-1 primary condition come from a fundamental point of view? It was that we were only allowed to do while invariant path integrals. Now you remember that you've got a scalar operator. A scalar operator, how it transforms under conformal transformations, it's a mystery if it transforms anything but like invariant. Because, you know, if you don't understand conformal transformations too well, you think conformal transformations are just some diffeomorphisms. And a scalar transforms is invariant under diffeomorphism. But we are not like those guys who understand conformal transformations only half, right? We understand them fully. And we know that conformal transformations are compounding a diffeomorphism and a Weyl transformation. Since scalars transform trivially under diffeomorphisms, all of the transformations, this 1-1 nature comes from the Weyl transformation. Okay? And therefore, this, in fact, we checked this multiple occasions last semester. This 1-1 nature is simply exactly the same transformation under Weyl transformation that would exactly cancel the factors of square root g. Okay? So, and we use that under Weyl transformation, C's and C tildes were invariant. So now let me ask you, this is all just to jog your memory so that you, okay, let me ask you. These C's and C tilde, I just argued for you that because psi was 1-1, because V was 1-1, it told you that it transformed under Weyl transformations in a particular way. In fact, exactly in the way that will cancel square root g transformation. Now C times C tilde is also 1-1 operator. Why doesn't that mean that it is also transforms under Weyl transformations?
C came from this vector.
Exactly. C was a dimension 1 operator because a holomorphic vector field has dimension 1. So it's the diffeomorphisms that gave C dimension 1. So the Weyl transformations had nothing left to do. So it was invariant under Weyl transformations. Okay? So the fact that it's got some dimension is not enough to tell you what its Weyl transformation. It's not enough to tell you what its Weyl transformation is. The fact, once you know it's an operator, it's a primary. Oh, if you know it's descendant also, you know, but it's more complicated. Okay? If you know that an operator is a primary, be a scalar, see its Weyl transformations, then you immediately, see its dimensions, then you immediately know its Weyl transformations. Or more generally, if you know that it's a primary or any particular descendant, and you know how it transforms under conformal transformations, you can figure out how it would transform under Weyl transformations. Just by undoing it, right? Because the whole thing, the conformal transformation is a product of diffeomorphisms and Weyl transformations. Subtract off the diffeomorphism part, what's left is the Weyl transformation part. Okay? And the fact that it was a primary was related to the fact that it transformed homogeneously under Weyl transformations. You see, suppose you have an operator that under Weyl transformations goes like e to the power 2 phi times O. Now let me take the derivative of the operator. It will have a term that goes like e to the power 2 phi times O, but it will have another term that goes like del mu phi times O times e to the power 2 phi times O. So descendants in general transform non-homogeneously under Weyl transformations, which means that they had transformed involving factors of derivatives of this Weyl factor. Okay? However, it's just primaries that transformed without these complicated things. If you had any of these complicated things, it would kill you in this formula. There's no hope it would be a invariant under Weyl transformations. Okay? So the primarality was the statement that it transformed homogeneously. The 1-1 was the statement that its transformation killed the transformation of square root g. Okay? Of course, there are many other ways of understanding it, but just at the most straightforward level, you can look at the formula and see that. Okay? Great. So, so this formula we completely understood, and now let's get back to a quick review of the fermions. Okay, so we had these so-called left-moving or holomorphic fermions, the so-called right-moving or anti-holomorphic fermions. Now, why were there fermions at all? It was that we decided that we want to gauge more, we want a larger symmetry algebra on the world sheet of the string than the symmetry algebra that we had. Now, the symmetry algebra is one point of view, but there's more fundamentally. Where did the symmetry algebra come from? It came from the fact that we were studying 2D gravity coupled to matter. Okay? And we demanded that our gravity theory be Weil invariant. Why do I say we were studying 2D gravity coupled to matter? Because we were doing a path integral over world sheet metrics and world sheet matter fields. Why do I say we demanded Weil invariance? Because we demanded Weil invariance. Okay, you remember, why did we demand Weil invariance, somebody?
Yeah, because it was a fake thing that we got by going to the Polyakov action, which is not a real symmetry of the theory, so it had better...
Exactly, exactly. You know, a gauge transformation is a redundancy of description. Now, the best way of generating a redundancy of description is to start with a non-redundant description and to put it in. And that's what we did. The number go to action was non-redundant, but description was non-redundant in the sense that it had diffeomorphism redundancies, but no others. And then we found that it was non-redundant but irritating. Okay, I mean, we couldn't do much with it. But then we reduced it to a redundant but simple theory. Okay? Now, if we wanted to be quantizing the number go to action, and we did it from the point of view of this simpler 2D gravity point of view, it had to be 2D gravity modded out by Weil transformations. That was necessary logically. It was also very pleasant. Because, you know, gravity theories are sort of hard to deal with. But 2D gravity modded out by Weil transformations is nothing. Because there are 3 metric fields and 3 symmetries. But you know, whenever you have a gauge symmetry, you can get rid of degrees of freedom by gauging. But then there's also the equations of motion that those degrees of freedom that you had got rid of would have imposed on your system, that now have to be imposed as constraints on what's left behind. Okay? That constraint system was in particular the statement that the annihilation part of the stress tensor kill our system. Because the equation of motion for the metric was the stress tensor. Okay? And that, in poor man's language, was the reason that we had this whole constraint business, this whole BRST stuff. Of course, we went through it all with great detail. You understand the formalism very clearly. It was the BRST. Okay? So we had some constraint algebra, a BRST symmetry based on a constraint algebra. That constraint algebra, what was its source? Its source was that we had to impose equations of motion coming from varying the metric as equations of motion coming from varying the metric as constraints. Okay? And that constraint algebra was the basic formalism which we implemented with a particular theory, namely free bosons. We could have implemented it, as we probably briefly discussed, with any C equals 24 times R11 theory. I say C equals 24 times R11 because our proof of our no-goes theorem required us to have x plus and x minus. You remember our no-goes theorem? That x plus and x minus played a special role. X plus s minus times any unitary C equals 24 theory would have worked in our no-goes theorem. Okay? So, any world sheet conformal field theory with C equals 24 times R plus and R minus times the free R plus R minus at least would have worked. Maybe more will work, but at least this would have worked. Okay? And our general structure, basic general structure, was based on the symmetry algebra associated with, based on the BRST invariance associated with symmetry algebra associated with this Virasoro algebra. Okay? All that was great. Now we decided that but the thing about it that was not nice was that our attempt didn't at least in flat space, where the C equals 24 field theory was just free bosons. No matter what we did, we always appeared to have a tachyon in a spectrum. And you know, it doesn't look like any fooling around with the C equals 24 field theory will help, because the tachyon was just dual to the identity operator on the world sheet. And every unitary conformal field theory has an identity operator. And you'll always have the same problem. You choose V to be this identity operator. And then to make it 1, 1, you will have to choose K squared to be tachyonic with this tachyonic mass. Okay? That seems like just a very generic problem. Like it does. So this formalism, while it looked very beautiful, didn't work. It didn't give us a stable theory of gravity. So, it could have been one of the long list of things that didn't work in gravity, loop quantum gravity. Many things didn't work. Okay? And had it ended here, it wouldn't have worked. But the question was, can we use the same idea? People ask the following question: can we use the same idea but with some detail changed to get something that does work?
I have a question. I
Yes.
can't remember whether I have asked this.
Yes.
So, is there any other way apart from introducing worldsheet supersymmetry of incorporating fermions into the theory and at the same time getting rid of tachyons?
Yeah.
so-
Yeah. Nobody knows of any other way. Oh, never say never. Who knows? But nobody knows. In fact, okay. Our attempt, as Upmanyu presaged and as we discussed at the end of the last semester, was to change the symmetry algebra. So and the way we were going to do it was to go back to the basics. We started with a theory that was gravity coupled to matter. We decided instead we will start with a theory which is supergravity coupled to matter. Okay? The supersymmetry in question was 1, 1, at least to start with, which means 1 supercharge on the left, in the left moving part of the algebra, and 1 supercharge on the right. And painstakingly and sort of a little, unpleasantly, at the end of the last class, we developed A, a superfield formalism, B, and you remind me if we did all of these things. But I think what we, if I remember right, A, we took the X worldsheet theory and looked at a superfield for it. You remember there was an X superfield which was X plus theta psi plus theta bar psi bar plus theta bar F. And we wrote down a worldsheet action for this X worldsheet theory, which was effectively d theta x d theta bar x d2 theta. Okay. Then we use this as a springing board for defining the more general structure of superconformal field theories. The superconformal field theories that we had a super stress tensor, some curly T. I know. Okay, curly T is equal to TF plus theta T. You remember this? And we generalize the operator product expansion of the bosonic theory heroically. We generalize this to include all these theta terms. Okay, if somebody has their notes, we'd be able to reproduce it in superspace. Polchinski doesn't have it, and I've totally forgotten it. So we'd have to work it out again. But the main point was that after doing this generalization, we found what that meant for the OPs of the components. Okay, we got it wrong, then we got it right. I don't know if you remember all that. Anyway, finally we matched Polchinski. We got some normalizations wrong, if you remember. Then we got the normalizations right, and finally we got it all to match Polchinski. So now, in this semester, we take the point of view, we've done the dirty work. We'll use Polchinski's answers. Okay? Schematically, we'll study it in much less schematically, but schematically, what was the form? T with T of Z with T of 0 was as usual, right? C by 2 divided by Z to the 4 plus 2t divided by z squared plus del t by z. Okay. What about t of z with tf of 0? Well, Tf of 0 was just a primary of dimension 3 halves. So that was 3 by 2 Tf of 0 by z squared.
So this is TP in other words.
T is Tp, sorry. Yeah, let me just write T,
Yeah.
T for Tp, if you don't mind. Del T divided by Z. The most interesting relationship was in TF, which was totally new. These are not new, right? These could have guessed. But what we got that was interesting was TF. So this is dimension 3 halves, 3 halves. Okay? So what you could have is something of order Z cube. Now, in TB, we couldn't have had a Z cube term because TB was symmetric under interchange. But this is odd under interchange. So you exactly can have a Z cube term. And this came with some factor. Let's write it down. What, do you remember what it is? C by 4 or something like that. T by Z, exactly. Yes, 3 by, okay, for C equals, C hat equals, okay, now we have to be a bit careful here. Yeah, when C is equal to 3 by 2, he got, well, C, he gets D by Z cube. So that's 2 by 3 C. Because D, now our theory, he was working with the free boson free fermion. Our theory has central charge equals 3 by 2D. Because every dimension has one boson and one fermion. And that gives you the central charge equals 3 halves. Okay, so 3 by 2C plus TB 2 T by Z. Okay, this was the general structure of the n equals 1 comma 1 superconformal algebra that we are going to use a lot in this semester. Okay, we also put the ghosts into supermultiplets. Do you remember that? Yes, exactly. For every B there was a beta, for every C there was a gamma. We put them into supermultiplets. We then we worked out the OP of these superfields and used that to deduce what the beta gamma OPs had to be. And beta gamma OPs were very similar to BC OPs. You remember B of Z, C of 0 was 1 by Z or 1 by Z plus dot dot dot. Okay? Remember C of Z, B of 0 was also 1 by Z. And you might think this is odd, but it's associated with them being Grassmann. Okay? Now, the beta gammas, because they have a theta relative to B and C, are now Grassmann even. Okay? So their OPs were, one of these was the same, but the other one was the negative of the, and now which one was which? Let's see. Beta gamma was minus, exactly. Okay, so beta of Z, gamma of 0 was minus 1 by Z plus dot dot dot, and gamma of Z, beta of 0 was 1 by Z plus dot dot dot. Okay? You remember that we computed the central charge of the beta gamma system and found that it was minus 15. I mean of the BC plus beta gamma. Okay. Okay, which means since BC was minus 26, it means that the beta gamma central charge was, 11. So the whole thing was minus 15. Okay? And that told us that string theory based on such a system, okay, would be consistent provided a matter central charge was 15, which means the matter dimension was 10. Okay? You remember that just like beta had, so just like C had its origin in world sheet diffeomorphisms, okay, gamma had its origin, C goes with gamma, yeah. So gamma has its origin in local supersymmetric transformations of the world sheet. Gamma was a fermionic gauge parameter, just like C was a bosonic gauge parameter. It had its origin. Each of these have reverse statistics to the actual gauge fields because they're ghosts. The Faddeev-Popov trick is used to put the determinant up or down that reverses their statistics. Just as B was essentially the graviton. Right? It was the change in the graviton, more precisely. Do you remember where did B come from? If you have a gauge fixing condition.
It was multiplying the change in metric.
Exactly. It was multiplying the change in the metric. So it was B delta C. This is the change in the metric due to the infinitesimal gauge transformation parameter, and this is B. So it was basically at the same quantum numbers as a metric. But B delta C. Now this delta C will have this derivative and so on, right? Right? It came. You remember we got the Faddeev-Popov determinant from. Okay. Exactly. This delta C came from the gauge transformations. The gauge transformations, it's the small diffeomorphisms.
And then the B somehow matched up
Yeah.
with the gauge.
Yeah, this delta C was what? It was the fact that under a diffeomorphism, the metric changes by del mu zeta nu. Okay, so in flat coordinates, this is del alpha zeta beta symmetrized, and then the trace part was removed because of the Weil transformations. So it was then we went to holomorphic, anti-holomorphic coordinates. It was just del C. Right? Okay. Great. Okay, so in a similar way, gamma has its origin in infinitesimal local supersymmetries, and beta has its origin in the gaugino. It's the thing that multiplies the change in the gaugino. Gaugino is the fermionic superpartner of the metric, and it's a spin 3 half field. Okay, so beta was a dimension 3 halves field, whereas gamma was a dimension minus half field. Okay, just like because it was like half of a vector. Okay, great. So all this we understood, and the first proper class that we start next week, what we will do is now to try to use this new symmetry algebra to build a new BRST charge and get a new physical state condition and to interpret that. Okay, that's our program. But there is one little technicality. There is one thing in proceeding with our analysis. There is one little bit of conformal field theory that will be very useful for us, and that's what my plan was for this class. Except I got a bit derailed into this summary. But let me start it anyway. Okay, and this little technicality is this beautiful thing about 2D CFT called bosonization. Okay, so my plan for this class, though I'm going to have to go soon, so we may not get through it all, is to study bosonization. Okay, so before we start this, maybe we should, since Sunil is now here, we need to decide on the timings for the class from next week. That was one of the main reasons for having this meeting. So people come out with proposals. So one proposal was
Monday afternoon and Wednesday afternoon.
one Monday and Wednesday afternoon. If the class works, does that work for everyone?
Monday timings, exactly.
Timings, proposed timings. Are there timings you cannot make?
Before 4:15 the class has to be.
Before 4:15. Okay, that's good. On Wednesday, are there constraints?
Again, same.
Before 4:15. Okay.
So class is
Yeah. Monday shouldn't happen then because the QST. Yeah. Tuesday we have a slot. Let's not mess with that if it's convenient with everyone else. What about trying Thursday?
Thursday afternoon there's a class.
What about Thursday morning? 11 o'clock.
That
Might be an issue.
Okay, Thursday morning is okay.
Manu doesn't like.
No, I mean
Yeah.
every day.
Yeah, you have to meet your advisor in the morning. Yeah, same problem. Okay, so if we cannot find another thing, we'll just continue with what we have, Tuesdays and Fridays.
Friday in the evening?
Evening, I can't. I mean, there's no other proposal.
5:15, 5:30.
5:15, 5:30.
Yeah,
5:15 is fine? Okay, so unless somebody comes up with another concrete plan, we'll stick with Tuesdays and Fridays. I don't care, you guys decide.
Tuesday.
Okay? Tuesdays and Fridays is what?
Tuesday at what time?
2:30. Okay, so then in the next class, where we really properly start the stuff, will be Tuesday 2:30 in the coming week. Okay, but I want to just maybe 10 minutes more. I wanted to tell you about this thing about bosonization.
Friday 5 or 5:15? What did you say?
5:15. Okay, you will see that this is an extremely useful thing in the study of worldsheet string theory, but more generally, it's an extremely useful thing for every study of two-dimensional conformal field theory.
I have a question.
Go on.
You are building supersymmetric theories,
Yes, on the worldsheet. Yes.
and on the worldsheet, as long as you maintain supersymmetry,
Yes.
you are going to get Hilbert space with positive energies. I mean, apart from Hackworm, I am saying the negatives will go away, as long as you maintain. But is there any spontaneous supersymmetry looking mechanism? No potential, right?
No. We're doing at least the theories we're looking at are extremely simple. Like at least the canonical theory is just free.
They are free theories, so
Free
you
theories.
have no way of spontaneously.
However, we do have a way of explicitly breaking supersymmetry, which is by choosing boundary conditions for the fermions that break supersymmetry.
The boundary conditions might break.
Yeah, and I didn't go through that in my review, but if you remember, we went through this
Yes.
a little bit.
Nebuchadnezzar and
There were two possible boundary conditions for the fermions.
R and NS.
R and NS.
Choosing differently will be like breaking breaking some sort of a Lorentz invariance or something.
Supersymmetry. Well,
No, if you do not choose RR or NS,
Ah.
you choose R and NS. It is like you're deciding to give some priorities of some.
well, in space-time, you will get fermions. Let me remind you of this. This is an important part. Firstly, what was R and NS? R was periodic boundary conditions for the fermions on the cylinder. NS was anti-periodic boundary conditions. Okay?
R was antiperiodic on the plane.
R was antiperiodic on the plane. Yes. Let's review that. Where does Indranil's comment come from? What?
Divergence has a square root.
Exactly. It's basically the fact that if you want to write the worldsheet, the cylinder oscillators on the plane, you will write psi is equal to psi r by z to the power r plus half. This half is put here so that if you do the conformal transformation, the Weil transformation that takes you back to the cylinder, that half goes away. And then z to the power r becomes z to the power r in space becomes e to the power I r sigma. Okay, and the time dependence just becomes e to the power IRT. It's IR log mod z. You remember all that, right? Go to Lorentzian space, it's IRT. Okay, so this business here, this half is crucial Because suppose we had something that was e to the power IR sigma on the cylinder. So in the Neveu-Schwarz sector, R is half integral on the cylinder. So these R's are half integral. So NS, R belongs to Z plus half. Whereas in the Raman sector, R belongs to Z. Right? Because R's are cylinder labels. They give you the Fourier mode on the cylinder. And I told you the boundary conditions of the string as they are on the cylinder. But the transformation does something. You might have thought that the weird guys were the NS guys, because they're antiperiodic along the circle. And the simple guys are the Raman guys, because they're periodic on the circle. Those sound like they should be the nice things. But look what happens to them when they go to the plane. These guys, the NS guys, are expanded in integer powers of R. Whereas the Raman guys are expanded in half integral powers of R.
Where did that factor of half come from?
It came from the conformal transformation.
Just dimensionality?
Yeah, let's remind ourselves where it came from. Exactly, just dimensionality.
That's only engineering dimension.
Engineering dimensions, but let's remember how primary operator transformed under conformal transformations. Okay, so first let's remember what the conformal transformation from the plane to the cylinder was. Suppose I have e to the power, so there's sigma and t, let's say, are cylinder coordinates. Okay, then we define W to be I sigma plus t, let's say. I can't remember if this was our definition, but let's say it is. W to be I sigma plus t in Lorentzian Euclidean space of the cylinder. Okay, and then Z was equal to e to the power W. So that late times, yeah, perfect.
Yeah. Yes.
Okay. Now, the rule for a dimension R operator is it transforms like, the same power as a derivative transforms to the power R. Okay, so del W is equal to del W by del Z. That tells you that a primary operator in the W frame is equal to del W by del Z to the power R, if it's dimension R, times the primary operator in the Z frame. This is the rule for operator transformation. This is just a quick way of remembering it. Okay, so now let's figure out what psi W is in terms of psi R. Let's use this formula. Psi Z, let's use this formula. Since we've got Z as a function of W, it will be easier to do the reverse thing. So phi Z is equal to del Z by del W times phi W, and this case to the power half. Now del Z by del W is Z to the power half, because R was half. Right, because psi was a dimension half operator. Okay, but Z was just e to the power W. Its derivative is still e to the power W. So this is just square root of Z times phi W. So what, and why have I got that? Have I got that wrong or right? I wanted square root of Z. I wanted the other way around, right? Because this del phi W.
The del W is not matching with the del W del Z. That should be del Z.
Thank you. Sorry about that. I got my derivative transformation wrong. Thank you. Okay. Del Z, anyway, 1 by square root Z. So square root Z times phi Z is the operator on the cylinder. That's this. And that's the power of Z to the half. Okay, so that's the reason. Okay, great. Great. So, what's the lesson for this? This is something all of which we're going to go through in great detail over the next few classes. But what's the lesson for this? It means that any state in the Raymond sector, okay, a state in the Raymond sector of the fermion theory is going to map to an operator that you get by mode expanding psi in half integer powers. Okay? Whereas a state in the so it's going to be a sort of weird state. It's Raymond sector state. The Raymond sector state. We'll work it out in great detail by state operator map. Okay. Should I do it now? Okay. Well, let's go according to plan. We'll work it out in great detail by state operator map. Okay. Whereas the state in the NS sector will be something nice and simple. It'll be sort of like del X. Okay. So let's just illustrate. Actually, we need the bosonization to work it out for the simplest way is to use bosonization. That's why I'm introducing bosonization for the Raman sector. But
This zero modes, this Rs has zeros. Rs has zeros, right?
excellent.
He is quantizing on the cylinder.
Excellent.
But cylinder levels matter, and in the cylinder R has integers.
Exactly. So R also has zero modes. This is an excellent question that Indranil raised. And let's remind you, in fact, this was my motivation, if you remember, for introducing fermions in the world sheet. It was because, at least in the Raman sector, fermions have zero modes. Why was that a good thing? The good thing was that the...
But this is related to your quantizing of the cylinder.
Yes?
This is what...
Yes, you're quantizing on the cylinder.
And we are looking at spectrum of Hamiltonian on the cylinder.
Yes, that's always what we have to do, because that's what the string does. Right? It's on the cylinder. The plane is a trick to calculate. Cylinder is physics. Right? Okay, so the
Can I continue this?
sure.